Okay, this is part two of the chapter 5 study guide. So we're talking about just the structure of Pascal's triangle. It's really useful for answering questions about the binomial theorem. So off on the side here we'll kind of draw Pascal's triangle. So remember, it starts with a 1 and some ones here, and then it's 1, 2, 1. And here's where that 2 pops up from. If you take this one and add it to this one, you get 2. And that's how you build all the internal parts of the Pascal's triangle. The edges are like the kind of like the sides of the pyramid here are always ones, but the interior is always constructed by adding the numbers that are like top left and top right of that. So the next one is 1 3 3 1, 1 4 6 4 1. You can see the 6 came from adding 3 3, so on and so forth. So you should be able to generate, if I give you part of Pascal's triangle, you should be able to generate the next row. So on the test, I'll actually have part of Pascal's triangle on there. But say maybe I'll have like the first 6 rows of it, but I'll ask you to generate like the 7th or 8th, for example. So, or maybe I'll have the first 8 and you generate like the next 9th and 10th, something like that. But it keeps generating by adding those numbers, so on and so forth. So how many numbers in the 8th row of Pascal's triangle? Well, first of all, you can actually answer this question without even generating the 8th row. If you notice, like this, if we call this the first row, there's the first row right there, then you know that in the 8th, like in the second row, there's 2 numbers, the third row, there's 3. So obviously in the 8th row, there's got to be 8 numbers. Now, what that represents, though, I actually like to call this the 0th row. I like to think of this one as the first row because this is like the first power, and this is like the second power, and this is the third power. So even though it says 8th row, like to me, what might be called the 8th row of Pascal's triangle, I think of it as sort of like the 7th power row of Pascal's triangle. But either way, there's going to be 8 numbers in there. But you can even, if you generate first, second, third, fourth, fifth, sixth, seventh, 8th row, you can just count the numbers if you want to generate it and see that there are 8 numbers in that. Or actually, so here's the thing, since the 8th row is the one that begins with the 8th power, technically there are 9 rows. So this is not the first, this is the 0th row. This is the second row. This one, I'm sorry, this is the first row, this is the second row. The third row, even though you might count it and think that it's the 4th row, I'm going to have these labeled on the test just so there's no confusion. The quote unquote first row, we're to call that the 0th row. So there's actually 9 numbers in the 8th row of Pascal's triangle. Now, if you wanted to answer the next question, which asks what are the numbers in the 8th row of Pascal's triangle? So this is the 4th row, 5th row, 6th row, 7th row, 8th row. That way you have to actually generate it out that way. So those numbers are 1, 8, 28, 46, 70. But 70, is like the middle there. And then 46 again, 28 again, 8 again, and 1 again. Notice how there's a kind of symmetry to that. Again, the 8th row, even though you might count it as a 9th row, it's the one that begins. It's the one that doesn't begin, but it has an 8 right after the leading one. Let's look at number 70. All right, the next one asks how many numbers in the 15th row of the triangle. Now, I am not going to generate up to the 15th row. That is insane. But notice how since the 0th row has 1, the first row has 2, the second row has 3 numbers. Well, I know the 15th row is going to have 16. In fact, let's make it more interesting. How many numbers are in the 971st row of Pascal's triangle? Well, if you guessed 972, you would be right. So whatever row they are, whatever the amount of numbers or the number of numbers that are in there is equal to that row plus 1. And that's crime, baby. Okay, 71 is kind of a fun one. Again, you can generate it by generating the 15 rows, but let me show you something that you may have never noticed on Pascal's triangle. So we want to know just the third number, not all the numbers, but the third number on the 15th row of Pascal's triangle. And let me show you something interesting. Notice how the first number is always 1. So we know the first number is 1. And the next number would obviously be 15. The third number is a lot more complicated. So, but let's look at the third numbers of the rows now. I mean, the third number here is 1, then it's 3, then it's 6, 10, 15, 21, 28. Now, you might not see a pattern, but look at this. If you add 2 to 1, you get 3. If you add 3 to 6, if you add 3 to 3, you get 6. Add 4 to that, you get 10. Add 5 to you get 15. Add 6, you get 21. Add 7, you get 28. So here's the thing. I don't want to know all the numbers of the 15th row. I just want to know the third number. So I know there's going to be like 1, and there's a 10, 1, 11, 1, 12, 1, 13, 1, 14, and then here 1 and 15. And I'm just going to generate the next number. So 21 plus 7 is 28. So if I add 8 to that, I get 36. And if I add 9 to that, I get 45. For this one, the next one, you add 10 and you get 55. You add 11 to that and you get 66. You add 12 to that and you get 88. Add 13 to that and you get um you get 94, and then you add 14 to that. Now here's an easier way you could have done this. Instead of like seeing what all that is, you could have just noticed that, oh hey, well, obviously just start from whatever row you left off on. You could take this, let's say for instance, take this 28 right here. Do 28, oops, do 28 plus, and that's on the 8th row, 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14. I know that once I add the 14, I'm on the 15th row, and so you get the number 105. So just a neat little trick. So it's really just an exercise in patterns there. So this one actually comes out to 105. And notice how I didn't have to find all those intermediary results. I could have just used this little pattern here, this little inductive reasoning to figure it out. So that's how you do one like 71. This I can tell you would probably be like either multiple choice question or a bonus question. So just this isn't super practical outside of just cool things with patterns, but it's not crucial that you this doesn't have a lot of applications for other things other than just patterns. Okay, the real application of the binomial theorem, and specifically of Pascal's triangle, is when you're trying to expand a binomial. So, say you want to raise a binomial to the third power. Yeah, you could write the x plus 9 3 times, and then you could a lot of people say FOIL it, and you could take that and FOIL again, but that's a pretty inefficient way to do it. Using Pascal's triangle and using the binomial theorem, we can do this a lot more efficiently. Now, we know that the third row of Pascal's triangle is a 1, a 2, and a 1, and the binomial theorem works this way. We're going to take that coefficient so we're going to take that 1, and then what we're going to do is we're going to take the x, we're going to raise that to the third power. Now, you won't see this in the binomial theorem, but I like to put it. This is like the a, and this is like the b. The b is not going to be raised to any power at all, or to the 0th power. The next term, I'm going to pull the second coefficient, the 2. Then I'm going to take this a, which is the x, really. That's going to go to the 2nd power. Then the b, which is the 9, that's going to be to the 1st power. So these powers go down while the other powers go up. So next, we're going to have, oops, actually I have the wrong coefficients here. Third, that's the second power row, 1, 3, 3, 1. So there's going to be a 1, a 3, and a 1. And then the powers of x are going to go down, x third, x second, x first. And then a lot of people won't write that x0. I like to. The powers of 9 go up instead of down. 9 to the 0, 9 to the 1, 9 to the second, 9 to the third. And since there's a plus, all of them are going to be plus. If this were a negative, which you'll see in a later example, the signs will alternate positive and negative. But this is your unsimplified answer. So 1 x to the third, 9 to the 0, 9 to the 0 is 1. 1 times x to the third, I can just write x to the third. Plus, well, I got a 3 times a 9 to the first, so that's 3 times 9, so that's 27. And then there's an x squared. Plus, let's see, 9 squared is 81. Then I got to do 81 times 3. I'm actually going to calculate that. 81 times 3. So that's going to be 243. I can write x to the first, but I'm just going to write x. You can write the 1 if you want. There's nothing wrong with that. Abby specifically, she might like have that. She hates ones that feel all left out. This x to the 0 is just 1, and that's 1 times 1, so that's just 1. So really just 9 to the third, which you can do 9 to the third on your calculator by using the little caret function. So that would be 729. So this expanded binomial would come out to this as a polynomial in standard form. So that's number 72. All right, now for the fourth power, we're going to need to use the next row of Pascal's triangle. This is we call it the fourth row, even though it's the fifth row. Again, we call the first row the 0th row, then we call this the first row, and then so on and so forth. So the coefficients we're going to use are 1, 4, 6, 4, and 1. And then we're going to start with b to the fourth power, and then go just like we would the x, and then go b to the fourth, third, second, first, and no power. And the 2, we're going to start not raising it to any power, or to the 0th power. Then ascend with that 1, 2, 3, and 4. So you can do it any way you want. You can do them one term at a time. I sometimes like to, I'm going to put a coefficient. I'm going to put whatever the first thing is to a certain power, and then whatever the second thing is to a power, and I'm going to put a plus or a minus. And I'll put the 4, a blank, and a blank, plus a 6, and I'm getting these coefficients for Pascal's triangle, a blank and a blank, plus another 4, a blank and a blank, and plus the 1, a blank and a blank. Sounds like I'm censoring a swear word there, but I'm not. I literally just mean blank. So b is going to start off to the fourth power, then b is going to go to the third power, then b is going to go to and I'll actually color code. So b will be to the fourth, then the third, then the second, then to the first. You don't have to write the 1. I like to write it here. I don't write it in my final answer. And then b to the 0. You can choose just not to write a b at all because b to the 0. But the other powers will start low. So 2 to the 0, which of course is just, it's just 1. That's why I'm canceling out. When you multiply by 1, nothing happens. Then it's 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. And this is not wrong, but it's just not simplified. So we want to take those numbers and simplify it. So this is just b to the fourth plus 4 times 2 is 8, so that's 8b cubed. 2 squared is 4, times 6 is 24, so 24b squared. 2 to the third is 8, 8 times 4, 32. B to the first, again, I'm not writing the first this time, plus, and then 2 to the fourth is 16, 16 times 1, and then that's times another 1, because b to the 0 is 1. So you get just 16, so number 73. When you expand it, you get this binomial. So hopefully you've got the strategy by now. We're going to practice 2 more. Okay, this one's going to use the third row. The third row of Pascal's triangle is the one that the second number is a 3. And if you remember, that one is 1, 3, 3, 1. Okay, so I'm going to go ahead and I'm going to do a different strategy. I'm going to do them one term at a time, just in case you prefer that. Put the coefficient. I'm going to take the 3a, and I'm going to raise that to the fourth power. But here's the thing. This is all the 3a terms. So take 3a and then raise it to the 4th. Take the 1 and raise it to the 0th power. Oh, sorry, not 4th power, not 4th power. This time it's 3rd power. Then I'm going to take the next coefficient, which is 3. Now 3a. I'm not going to do 3a to the second like that. The idea is the whole thing gets raised to the second. And then now it's times 1 to the 1st power. Then I'm going to take the next coefficient, which is 3 again. And then now 3a goes 1 power even further down. So 3a to the 1st, writing the 1 is optional, of course. Then it's 1 to the 2nd power plus, and the last coefficient is 1. That's the last term. There's only 4 terms in the 3rd row of Pascal's triangle. So that one's just 3a to the 0th. But when you raise something to the 0 power, it just, anything to the 0 power is 1 with the exception of 0 itself. And then times 1 to the 3rd. Now, this is easy because 1 to any power is 1. The only thing I really have to do work with is this 3a to the 3rd. Now, a to the 3rd power is a to the 3rd. 3 to the 3rd power, because the idea is the exponent kind of distributes here. 3 times 3 is 9. 9 times 3, 27. So 27a to the 3rd, and everything else multiplied by 1. Here I've got another 27, but for a different reason. I've got an a squared. 3 squared is 9. And then 9 times 3 is 27. So just kind of a coincidence. You happen to get two 27s there. Plus, and then now it's a to the 1st power, but I'm just going to write the a. 3 times 3 is 9. Plus, and then this is all just 1 because it's 1 times 1 times 1 times 1. So plus 1. So that is number 74 all expanded. Okay, we're going to do okay, this is the first one where there's a negative right there. Now, the only real difference when there's a negative, you'll kind of notice the pattern, is that these were all positive in the previous 3 examples, but there's going to be some that are negative, but some that are still positive, and you should know the pattern, how it goes already. But we're still in the 3rd row of Pascal's triangle, which means the coefficients are 1, 3, 3, 1. I'm going to go back to doing it the way I did 2 problems ago. 1, 3, 3, 1. Now I'm still going to put pluses here, even though I know better, but I'm going to show you why they're sometimes negative and sometimes not. So I'm going to start with the x term. We know that the first one is going to be an x to the 3rd, then x squared, then x to the 1st, and then x, to the 0 power, which means it's just 1. And then, but the 5 is times 5 to the 0, which of course we know is 1, times 5 to the 1st, 5 to the 2nd, times 5 to the 3rd right here. Now, but here's the thing, it's not really a 5. In a way, it's like a negative 5. So here's what I'm going to write. I'm going to put this in parentheses, negative 5 to the 1st power. Well, negative 5 to the 1st power, when you raise a negative to an odd exponent, 1 is an odd number, you get a negative number, or you could just say, hey, negative 5 times 3, there's a minus 15x squared. Hey, that's interesting. The second term is negative. The first term was positive. Well, how about the third term? Well, if you take a negative 5, but now you square it, a negative times a negative is a positive. They kind of cancel out. Oh, hey, it goes back somehow to being a plus. So this comes out to a 15x. And then this, again, this is a negative, right? But negative 5 to the 3rd, you can calculate in your calculator. If you don't know what negative 5 to the 3rd is, it's negative 125. But because it's raised to an odd exponent, that's why it stays being negative. So this could be minus, didn't want that in blue. So minus 125. Okay. Now, you should know this already from the practice and the homework. These always go positive, negative, positive, negative. Now, if there are like 8 terms, doesn't matter. Whatever power is raised to, notice how in the 3rd power there's 4 terms. If it were to the 19th power, and I'm not going to give you one of the tests that's even close to that high of a power, but if there were, a 19th power, it would still go positive, negative, positive, negative, positive, 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 negative, all the way through whenever there's a minus here. So you should expect that to happen. But if you just do, your arithmetic right, it should happen naturally. You don't have to force it. You don't have to memorize this. You should just know that naturally it's going to happen anyway. Okay, 77 is, I'm only going to go as high as the fifth power on the honors questions. So remember, those questions are only required if you're in the honors sections, and if you're not, those are worth possible extra points. But this one we're using so this was the third row of Pascal's triangle. This would be the fourth row of Pascal's triangle, but we're doing fifth power. So we're going to use the fifth row of Pascal's triangle. And I like to, it's convenient, this is a plus, so I know they're all going to be positive. I'm going to put the first coefficient and then a blank and a blank. I'm going to put the second coefficient, a blank and a blank. I'm going to put the third coefficient, blank and a blank. And then the 10 appears twice. That always happens on the odd numbered rows. You know, you're always going to have that asymmetry where there's not one number in the center, there's like two numbers in the center. And then we got another 5, a blank and a blank, and then we got a 1, blank and a blank. And then we're going to have 3a will start off to the fifth power, then 3a will be to the fourth power, then 3a will go to the third power, then 3a will go to the second power, then we'll have 3a to the first power, and then I write this, most people don't write this, 3a to the 0th power, which means it just cancels out to a 1. And then the 4b, that's the 0th power, which means it's like not there at all, basically. 4b to the first, put that in parentheses, that's important. 4b to the second, 4b to the third, 4b to the fourth, and 4b to the fifth. There's your answer right there. Now, it's not simplified, but you can get, most of the credit if you just know how to apply binomial theorem. You know how to set it up, that's great. Now, if you make some mistakes simplifying, you'll still get partial credit, but just kind of try to be careful here. There's a 1. I know that a is going to be to the fifth. I don't know what 3 to the fifth power is. I'd have to calculate that, but let me show you. Why not kind of preload what all these things for exponents are? Let me show you a way to do that in your calculator. There's an easy way and a hard way to do that. You could just, manually enter it in your calculator. Take 3, raise it to the fifth. Take 3, raise it to the fourth. You can do like that, but, just since we're using a calculator anyway to calculate this, not that it can't be calculated by hand, let me just do 3 to the x, okay? And for good measure, let's also do 4 to the x, because I care about powers of 4 as well. And I'm going to go into my table, and I want to raise those things to the first, second, third, fourth, and fifth powers. So those are the numbers that will be relevant. Again, I could have put them in my home screen. I decided to use my calculator to have like an organized way of seeing all the powers all in one place, so that I can just kind of plug them in. So I know that, this one represents powers of 3, this one represents powers of 4. So 3 to the fifth power is 243, and then the a is to the fifth. Plus, I'm going to have 5 times, now 3 to the fourth power is 81. That's this thing right here. And then 4 to the first power is obviously 1. Now the a is to the fourth. And then there's a b to the first, so I'm just going to write b. Plus, and then we got 10, and then now 3a to the third. So 3 to the third is 27. Oops, that's 10 times 27. And then 4 to the second, I know that one is 16. And then this one is going to be, instead of a fourth, b to the first, a to the third, b to the second. But no matter what, the powers have to always add up to 5. 5, 4 plus 1, 5, 3 plus 2, 5. Next term, now I'm doing 10 times, I know 3 squared is 9. I know 4 cubed is 64. But that one's a squared, b cubed. And then we have 5 times 3 to the first is just 3. I don't know offhand what 4 to the fourth power is. But since this is the 4 column, fourth power, so it's times 256. And that one's just an a, but then the b is to the fourth. And then there's one more term, which is going to be a just b to the fifth term, whatever 4 to the 5th is, which happens to be 1024, b to the 5th. So this is the answer a little bit more simplified. I just have to multiply these numbers out. You get 243 a to the 5th plus, I got to multiply 5 times 81 times, I don't have to put that 1. 5 times 81, just calculate what that is. It's going to be 405 maybe? Let's see, yay, 405. But, I got a calculator right there, why not use it? That's a fourth b term. Plus, this is 270 times 16. No, thank you, I don't want to calculate that. Let's use a calculator. So 10 times 27, I know that's 270. Then that times 16 is 4,320. So 4,320 a cubed b squared plus, this will be whatever 90 times 64 is. So that one will be 10 times 9 times 64, 5760. And that's the a squared b cubed term plus 5 times 3 times 256 is 3840. And that's the ab to the 4th term plus, and then this one's already simplified, 1024 b to the 4th power. So this is the binomial fully expanded and completely simplified. That's your final answer. Okay, so the last one was a 5th power. This is a 6th power. It might seem like, oh gosh, a 5th power, it was so complicated. This is going to be even worse, but actually this is going to be easier. The 5th row of Pascal's triangle was this. So the 6th row, we just kind of add those, coefficients. And so we get this right here. But here's what makes this problem actually easier than the last one. There's like the coefficient in front of the x is just 1 and 1 is a constant term. So we don't have to do any of the arithmetic. So we just write, you could just write the Pascal's triangle term. So it'd be 1 x to the 6. And then no matter what power you raise 1 to, it's 1 to the first power is just 1. So it's 1x to the 6 plus 6x to the 6 and or x to the 5th and then 1 to the first, right? But 1 to the first is just 1 plus, and then you have 15x to the 4th and then times 1 to the 2nd. But 1 to the 2nd is again is just 1. At this point, I'm going to stop writing the 1s. Then that's plus 20x to the 3rd times 1 to the 3rd, but it doesn't matter, plus 15x squared plus 6x plus 1. So this is actually your answer right there. And I don't need to write those 1s at all. This is just, and I could even erase this one too. But whenever you have the constant term is just a 1 and the coefficient on the variable term is a 1 too, you could just write the coefficients of Pascal's triangle and just start at your highest power of your variable and then go all the way down. That's it. 78, which is really, it's even though it's a 6th power, it's probably the easiest one here. All right, for number 80, we're only kind of partially working this out. All the work we did before is like, oh, this one's complicated because 3 and 4, that's so much work. But here's the thing, we only want to know the x squared term. Now, we know the first term is going to be the x cubed term. And then the next term is going to be the x squared term. And it's 1331. That's that's the 3rd row of the Pascal's triangle. And so we know we're going to be taking the we're going to be taking this thing right here. We're going to be squaring that, and then this thing right here we're going to be raising to the first power. So we're going to take 3x, we're going to square it, times 4, that's going to be to the first power. Notice how they add up to 3. And then the coefficient went with the first one, the x cubed term was just 1, 3x cubed, not that we care about the first term. But the second term is going to be the coefficient that goes with that as a 3. So this is the x squared term. And then we're just going to simplify that. There's a 3. 3x squared is 9x. The quantity 3x squared is 9x squared times a 4, and then you just simplify whatever 3 times 9 times 4 is, and we get 108. So the answer for that one is 108x squared. That's the answer. All right, so number 83, we're trying to find a linear, quadratic, and cubic model for this data. Now, I want you to know how to do this on your calculators. Real statisticians, they use spreadsheets to do this, and you can do this on spreadsheets. We've shown you how to do this in Desmos. But if you ever have a statistics course in college, if you have to do find a model of some equations, you're going to do this using your calculator. You're going to do this using some form of technology. So just to review, if you forgot how to, okay, and you can see the keys I'm going to press here. So the first thing I'm going to do to be able to enter these values, and I'm going to hit stat. So the stat button's right there below delete. Hit stat. Next thing you want to do to be able to put them in the little L1 and L2, the list, you're going to go to edit, which just hit enter. All right, now you want to put these numbers in there. If you have some stuff in here, I can just hit delete repeatedly. Just hit delete, 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 and deletes all those numbers out. But if you can also just overwrite them. So for the first column, yeah, I deleted them out, and I'm going to put these numbers in here, 15, 21. I'm not even going to bother deleting them for the second ones, and I'll show you why. If I just write over them, put a 7, hit enter. Notice how it writes over that previous number I had there. 11, hit enter. 26, hit enter. 44, hit enter. Now, here's when you'll be careful. Let's just say you had some random, other numbers after your last number. This would really mess things up. So if you do have numbers that go past your list, you do want to delete those out. Okay? But otherwise, you can just write over the previous numbers you have. Now, we want to do a linear, quadratic, and cubic model. We're going to use regression to do those models. So I'm going to start over just so you can see what the buttons are for that. You can hit stat. But then you're going to go over to the side. Notice how I hit the right arrow. You're going to go to linreg. And there's the linear model right there. And then you just do the same thing for quadratic and cubic reg. And we're going to see which model is better. So that's our linear model. To go to the quadratic model, you can go to quadratic instead and hit enter a bunch of times there. There's your quadratic model. And finally, for our cubic model, again, you just hit stat, go over to calc, and cubic reg, hit enter a bunch of times, and the cubic model pops up right there. Okay, now the thing to focus on here is that those R values or R squared values. Notice that, of course, on a cubic regression, the model is perfect. So technically, a cubic model does fit this perfectly because there's 4 points. The higher your polynomial, typically, the better that model is going to line up with the data really well. So, but let me just show you, we can look at what the other models, how well the other models do. If you look at the R squared value, this is 100% good if you think of it as a percentage. For the quadratic, it's 99.9% good. So here's the thing. The quadratic regression, even though the cubic model does it perfectly, yes, this is perfect because this is 100%. Here's the thing. With a cubic, this is 99.9% good. So even though the cubic model does it better, you wouldn't be wrong in saying, hey, let's use a quadratic model because it's just simpler. Now, one thing I want you to really get an idea of, well, how can you tell if these are models? I don't understand what this R value is. So let's actually look at the data. So we got these things in our stat thing, right? Let's look at these on a scatter plot. So I want you guys to go second, y equals. I want you to turn this scatter plot on. And everything else should kind of be set to scatter plot already. And I want you to hit zoom. And I want you to go down to zoom stat. What you'll notice is zoom 9. Instead of me hitting enter right here, I could be up here, but if I hit the number 9, it'll automatically do zoom stat. And notice how this thing, see how it's pretty clearly not aligned. I have some of my, let me clear these values out of here. I have some of my, those old things I was doing from a previous problem. But notice how a line equation, would not do so well. Let's just put a couple decimal places worth in here. Let's put this linear regression in here. 2.0. So go back to the y equals 2.08x minus 2.475 or 2.48. I can do that too. If I graph that line, see how the line, it doesn't do a terrible job. But the r squared value, you see how it's only 0.95? That line comes pretty close to comes really close to those points. It doesn't go through any of them. It doesn't go through all of them, not even one of them, but at least it kind of floats in between, so it's not terrible. But now let's look at the quadratic, okay? If we put the quadratic equation in there, so I'm going to put that one in y2. I'm going to make the linear one disappear. Crying baby. All right, and so we put 0.086. I'm just doing 2 decimal places, so I'm not doing even the full true regression here. So x squared plus the second one is 0.00. I'm gonna go more decimal places because like before that, like they kind of do nothing. X, and I'm gonna do plus the c value is 5.96. That's good enough. See how this hits the data. Wow, it goes through perfect. It almost hits that. It hits this pretty much perfectly. So yes, the cubic model, if I graph the cubic model, guess what? The cubic model would not only go through like 3 out of 4 of those points, or this one only seems to be going through 2 out of 4. If you did a cubic model, it would hit all 3 of those perfectly. But because this thing does so well, I would actually argue that due to the fact that a quadratic model is simpler, I would use the quadratic model. Now, you wouldn't be wrong if you said the cubic model. But because the quadratic model is, less complicated, and it works almost as good. And if you notice for the cubic model, see how the leading coefficient is a really, really tiny number, 0.00. You got to go 3 decimal places before you even get to a significant digit. So really the quadratic model or cubic model, both of those would be good answers to this question. Soon. All right, we're going to use cubic regression to model population here. So we're going to go to stat, and I'm going to go to that list that I had before. But here's the thing. We could use the number 2004, 2007, 2009, but they want us specifically to let X be the number of years after 2000. So the year 2001, we would just write a 1. The year 2002, we just write a 2. So instead of writing 2004, I'm just going to put 4. Instead of 2007, I'm just going to put 7. 9, 10, and it just makes it to where we can honestly you can just see the x-axis better, and the numbers from your regression just are not going to be as like intimidatingly big. So that's the reason why we do that. I'm going to put the y values into the L2 here, and we want to do a cubic regression. So we did that earlier. We're going to go to stat. We're going to go over to calc, cubic regression. And there's your cubic regression right there. And I will specify how many decimal places I want you to round to. But just as a general rule of thumb, you want to do like 2 or 3 decimal places. On the test, I'll only ask you to do 2 decimal places. So our cubic regression would be y is equal to negative 5.87x cubed plus 120.53x squared minus 629.27x plus 1421. That would be your answer right there. Now, if you want to see how well it models that data, since there's 4 points, we should expect it to model it perfectly, and the r squared value demonstrates that. If you don't see these r values, remember, you can get to that either by going to mode and scrolling down, and you turn stat diagnostics on, or you can go to catalog and you can go to the letter D, and you'll see diagnostics on right here, and you just like turn that on right there from the catalog. But you should have those turned on. I'll remind you to have that turned on before the test. But if we go to Zoom and we go to Zoom stat, which is option 9, these are the new points of data. So there's a point right here. But it's not graphing the line. Well, the reason it's not graphing the line is because I didn't put the equation. Here's the equation right there. I didn't put the equation in there. So if you go to y equals, again, I'm just going to do 2 decimal places. And I'm going to type in this with 2 decimal places. So there I'm putting into one of my y equals right there. There's the equation. And I have it set to zoom stat, the graph. And now when I graph it, oh, look how satisfying. Oh, man, it hits it perfectly. So and that's even, I did round to 2 decimal places. So it is possible that it wouldn't hit it perfectly, but that would be because of a rounding error, not because the cubic regression didn't do it perfectly. But that's how you do a cubic regression in your calculator. Okay, the last section of the test is this from 5.9. This is just more practice with transforming polynomials. We did this with absolute value functions and parabolas in vertex form. So let's take it one thing at a time. So if we have y equals x cubed, that's the parent function, y equals x cubed. If I want to reflect it across the y-axis, so if I want to do a reflection, that means only thing I'm going to change is it's going to have a negative, so it'll be negative x cubed. Okay, but then I want to take that and translate it 1 unit up. Well, that means to do that, I'm going to keep the negative x cubed. I already did that, but then I'm going to add the 1. So if you want to translate something 1 unit up, remember you're just adding something on at the end. Okay, but now I want to translate it 2 units right. And remember, you're going to need parentheses here. So I still have the y equals, and I still got the negative. But instead of like x cubed, it's going to be x either plus or minus something cubed. When you translate it 2 units right, it's not going to be a plus 2. It's going to be a minus 2. So the thing that translates it 2 units to the right is this minus 2 right here in the parentheses. So your final answer is y equals the negative reflects. The minus 2 shifts it right. Don't forget your cube outside the parentheses. The 1 shifts it 1 unit up. That's the answer to number 85. Just like we did with quadratics. Okay, number 86, again, the parent function we're assuming is y equals x cubed. I want to start with a vertical stretch by a factor of 6. A vertical stretch is when you put like the 6 in front. So this thing right here, vertical stretch, factor of 6, is putting like a 6 coefficient right here. A translation, if you're going to go left, 3 units left, you need the parentheses. So that's going to be when you have to have the x in parentheses. Now it's not x minus 3, it's x plus 3. So this would be your final answer. Y equals 6, that's a vertical stretch. X plus 3, that's moving it left 3 units. And it is a cubic function. So just to review, negatives reflected across the x-axis. In parentheses, a minus a number moves it right, plus a number moves it left. Plus 1 or plus a number on the outside moves it up. If you put a minus number, that would be how you translate it down. So that's 85 and 86. All right, last one, number 88. We want to take a fifth power function, that's the parent function, and we want to translate it 3 units up. We want to compress it, which is the opposite of vertical stretch, because the number is less than 1. Instead of making it like tall, it's going to make it short. So, all right, 3 units up. So think about what that is. You see, if it's 3 units down, it would be a minus 3 on the end. So 3 units up, it's going to be a plus 3 on the end. And then compressed by a factor of 0.3. That means you have like 0.3 x to the fifth. It's not moved to the left or right, so we don't need to put like the x to the fifth in parentheses. So your final answer is y equals 0.3 x to the fifth, translated 3 units up. There's your final answer. Alternatively, there's really no need for this, but if you really like fractions, you could say 3/10 x to the fifth plus 3, like that. But, I mean, they gave it to you as a decimal. Why not keep it as a decimal? All right, that's it for the Chapter 5 review.